Hello all, let's start section 6.1 and 6.2. 6.1 and 6.2 is about standard normal distribution, correct? If you remember, in our chapter 5, we covered probabilities that they were discrete, correct? It means they had finite number of values, correct? Discrete probabilities. If you remember, we covered this in chapter 5. Discrete means finite, correct? The good examples were dice, correct? Cards, and we did a lot of examples on these, correct? Because they were countable, they were finite. In chapter 6, we are covering continuous, and I'm going to start my lecture from here, continuous random variable. Random variable. Correct? First, continuous random variable is a variable that's not finite. The examples, if you remember from chapter 1, even I explained this for you in chapter 1, that there are two types of data. One of them is discrete or finite. The other one is continuous, that it has infinite solutions, correct? Or infinite here, if I talk about probabilities, infinite probabilities. I will do a lot of examples for you. For example, remember I draw a number line for you and I said, okay, if here I have 1, here I have 1.5, how many numbers are between 1 and 1.5? There are infinite numbers, correct? The best example is measurement or temperature, correct? When you say, oh, today is 85 degree, are we sure that it's exactly 85? It can be 85.1, it can be 85.01, it can be 85.001, right? There are infinite numbers that we call it what? Continuous. Now, if a continuous random variable has a bell shape, graph, correct? Bell shape means it's symmetric, right? This side is symmetric to the other side. We call this one a normal what? A normal distribution. A normal distribution. Now, to put these in words for you, I can write if a continuous random variable, if a continuous random variable has a symmetric bell shape, has a symmetric bell shape curve, it considered to have to have a normal distribution. Correct? If a continuous random variable has a bell-shaped graph, which is symmetric, we call that data what? A normal distribution. Now, slowly from here on, let's talk about uniform distribution. Uniform distribution. What is our goal today? Let me explain first our goal before even touching a uniform distribution. Today in 6.1 and 6.2, my goal is to connect or somehow translate the area under this curve. Under this curve, we know we have an area, right? The area under this curve. Translate the area as a probability. And also connect my probability to a number that we call it z-score. That's our goal. That's our goal, and I'll try to explain it for you how you can translate the area under this curve, bell-shaped curve, as a probability, and how to find the probabilities of continuous variables using z-score. Okay? That's our goal. This topic, part of it comes from calculus. Finding the area under the curve is a topic of calculus, but I'm not going to teach you here today calculus. I'll just explain it in a different way. And also we connect that to your book. You see on the left side of my screen that I already have the table of the z-score, and you can find this later. I'll tell you where it is in your book. It's the last 2 pages of your book. You can find this in your book, and also I'll teach you how to use calculator. Correct? Our goal is to translate area as a probability. To do that, let me erase this. I'll start with explaining what is uniform distribution. The word uniform means the same, military uniform, right? It means everything is the same. Then what is uniform distribution? All values, if we give a simple definition for it, all values have the same probability, of occurring. Correct? All values, they have the same probability. I'll explain it in a graph here for you. The name of this graph is density curve. Later I'll write the name also for you, correct? And I'll use an example to explain it. Let's think about our class. For example, every day I'll finish your class exactly, or every lecture exactly at 50 minutes, or sometimes we stay longer up to 52 minutes. Correct? Sometimes I take longer. I said, oh, let me just finish this lecture, then we can go. Correct? I can finish this class also at 51 minutes. Correct? Or I can finish it at 50.5. Here 51.5. Correct? I can finish this class at any time. 50 minutes, 50.5 minutes, but 51.5, 51, 52 minutes. But how many numbers are between 50 to 50.5? There are so many numbers, infinite numbers, correct? That's why it's continuous. That's why it's not discrete, it's continuous. I can finish at any time. Based on uniform distribution definition, I'm looking to the probability that I'm finishing your class today at 50 minutes, maybe 50.5 minutes, 51, 51.5, or 52. Based on this definition, all probabilities should have the same probability. It means if I mark here and I draw this line, my vertical axis is the probability. My horizontal axis is my x values, correct? All x values have the same probability. They are uniform. If I finish it at 50.5 minutes, you see the probability is the same. 51, probability the same. 51.5, probability is the same. 52 is the same. It's uniform. You see, it's a straight line. It's not a curve. Here I have a straight line, correct? This is a straight line. It's not a curve. That means I have the same probability for all values of x, correct? Now, such a probability, we call it what? A uniform probability, that all values of x have the same probability. Now, from here, if I do, when you draw this curve, which we call it density curve. This graph, the name of this graph is density curve. This density curve has two criteria, correct? Criteria number one, area, I mean the area of this rectangle in front of you, must equals to 1. It means if I shade this triangle, this area with the red shading, this area should be equal to what? To 1. This is the first criteria. Number two, criteria number two, height for each probability or height for each value of x, height for each value is greater equal 0 and less than equal to 1. Correct? Why? You see, the vertical axis, I name it probabilities. We know that probabilities should be always greater equal 0 and less than equal to what? To 1. Since chapter 4, I'm focusing on this, and I'm all the time asking you, what is the probability? It should be greater equal to 0 and less than equal to 1. This is the chance of happening something, correct? You can get 0 chance or higher and 100%, correct? You cannot have 110% chance of something, correct? All probabilities are between 0 and what? And 1. Now, if I ask you, let me clean the graph a little bit. Let me remove all these red shadings. If I ask you, what is the probability or what is the area exactly at 50.5? A question from algebra comes in. Can I find the area of a line? No, because line doesn't have a width, right? Then your area is always what? 0. But if I ask you, what is the area between 50 and 50.5, then it's really easy to find that, correct? Now, my question is, how, look, from 50 to 52, I have 2 units, right? From 50 to 52, moving there 2 units. Which number I should multiply with 2 to give me an area equal to 1? Correct? If you remember the area formula of a rectangle, A equals length times width. Then A equals, my length is 2 times, how much should be my height from here to here to give me, to multiply this with 2 and give me 1? Of course, it's 1/2, right? If I multiply 2 with 1/2, you see, these 2's cancels out, it gives me 1, correct? It means the probability of happening is always what? 1/2 for all these values, correct? Now, An example here. An example here. I want to do an example for you. Find probability that class will end between, you see, I'm giving you a range of numbers, correct? Between 51.5 minutes and 52 minutes. Because I'm talking about continuous, I cannot find the area of one line. I have to give you a range, correct? Here, if you see, if I draw my line from 51.5 minutes to how many minutes? 52. It means I'm asking you to find this area. Correct? From 51.5 to 52. How much is your distance from 51 to 52? It's 0.5, correct? And how much is your height? 1/2 means 0.5. To find that area, A equals actually here, your A equals 0.5, your height, times 0.5, your width, which gives you 0.25. It means 25%, right? Then the probability of finishing your class today between 51.5 and 52 minutes is how much? 25%. Correct? Did you see in these two examples, I translate the area as what? As probability. The area of this density curve is actually can represents the probability of happening something. Correct? Now, next thing that we want to discuss after this example, slowly we want to go to our normal distribution, correct? I will talk about normal distribution. Correct? We already know the graph of normal distribution is a bell shape. Correct? And the area under this graph since chapter 4, since we start graphing this, I told you the area under this curve is how much? 1. Correct? We call this one a normal distribution, a bell shape. And in the center, in the middle, we have always our mean. Correct? The mean is always at the center. It can be mu or it can be x bar, but here in 6.2, usually we are dealing with mu. Correct? Mu or x bar. The mean is always in the center. Correct? Now, look at this example. There are so many normal distributions. I can say infinite normal distribution curves around us. Correct? They're all normal distribution, but the shape is a little bit different. Here, my goal is to jump from normal distribution to a standard normal distribution. We want to standardize all of our normal distributions. Look at this example. For example, the average height for women is, if I graph it here, if I graph a normal distribution, the average height for a woman is 63.6 inches based on the data that I have from the book. The average height for a woman is 63.6 inches, and I'm sorry, somehow it's kind of, and the standard deviation is 2.5, correct? If I graph a bell shape, it's like this. I want to do the same time. I want to graph the average height for men, which is 69 inches, Of course, if it's 69, I want to graph it like this for men, correct? And the standard deviation for the men is, I think, 2.8 inches. Because you see here 2.8 inches means your data is more separated, correct? 2.5 inches because you have the data very closer to the mean, right? That's why you see the height of this normal distribution is a little bit higher than the one that actually 69 should be here in the middle, not there, correct? The height for the men is the height of the graph, not the height of the men. Of course, men are taller. The height of the graph is a little bit lower. Why? Because you have a bigger standard deviation. Your data is more separated here. What I'm trying to say, there are so many normal distributions. We want to right now standardize this normal distribution, correct? What I'm talking now is about standard, normal distribution. Agree? If I draw a curve for you, in a standard normal distribution, there are few things happening here. First, your mean is always 0. Your standard deviation is always 1. And the area under this curve is also always equal to 1. Correct? If I have this, if I have this, I can call this distribution that you see here, this graph, a standard normal distribution. You see, you remember this formula, x minus mu over standard deviation, correct? We named this formula after that as z-score. Z-score is actually this line, correct? It's a number that shows where is your data value, correct? For example, if I calculate f my x for normal distribution for women, f my x is also 63 point, what I use, 63.6, and the mean was also 63.6, correct? If I plug in this to this formula, you see 63.6 minus 63.6 over whatever the standard deviation was, which was 2.3, I think, it gives you 0 because 63.6 minus 63.6 gives you 0 over this number, which you end up with 0. That's why the mean for the standard deviation for time being, in this lecture is always 0. Correct? I will do only one example here, then I'll stop the lecture. I'll do part 2 for this lecture and we will do more examples. This example is about testing thermometers. Correct? A company is producing thermometers. They want to test their reading of their thermometers. How accurate is the reading of their thermometers? What they do, they put the thermometer in a sorry, in a ice water, and they just read how much the reading of this thermometer shows. Correct? In this example, the mean is 0 because when you plug in, or not plug in, when you put your thermometer in ice water, of course, the mean is 0, correct? 0 degree. Your standard deviation is 1, correct? And we want to test this thermometer, correct? Reading, I will put this for you, reading were normally distributed. Normally distributed. Find the probability, find the probability that a thermometer will have the reading of less than 1.58 degrees. To do that, you have to follow these steps. Now, steps how you're dealing with a problem like this. Step number 1, find z-score. And the formula is z equals x minus mu over what? Sigma. Step 2, draw picture. Draw picture doesn't mean draw any picture. It means draw this normal distribution always. Everything that right now we are dealing with, it's a normal distribution. Correct? Step 3, find the area. Using table in your book, which is table A2. At the last 2 pages of your book, I'll teach you how to use, or calculator. To use calculator, let me first explain. To use your calculator, second, correct, and variance. You see, I'll push on second, then variance, second. Variance, let me turn on, clear, second, variance, and you go to normal CDF. From here to normal CDF. I'll show it to you how. Look, if I go to normal CDF, which is this one, I'll come down, normal CDF, enter. They are asking you for lower range, upper range. You already see your mu is 0, your standard deviation is 1. Correct? For this particular problem, we have the upper value, which is 1.58 degrees. Correct? To find the z-score, you see, if I plug in for that particular 1.58 minus 0 over 1, which gives me 1.58, correct? I'll later show you how I do this, correct? But for time being, you have the right value, you have to enter the right, and you have to enter the left z-score. Right z-score and left z-score. For some problems, you only have one of them. For some of them, you have both of them to enter, correct? If you have the right value only, like this example, plug in negative 10 always for your left value. And if you have only left value and you don't have the right z-score, always plug in 10 for the right z-score, because you need a range to give to your calculator, correct? And it gives you the area. Now, let's solve the problem, the example. Step 1, I find the z-score. X is given to me as a 1.58. degrees, correct? I'll plug in the formula x minus mu over what? Sigma. Then z equals 1.58 minus our mean is always 0 because it's a standard normal distribution, and sigma is 1. Your mu is always 0 and standard deviation of 1. But later in 6.3, we gave you all these values. They are not 0 anymore, correct? Which you end up with 1.58. Step 2, draw. This step is really important. Students want, some of them like, why I should graph, but believe me, if you don't graph, you will miss everything. Always mark your 0. Now, where is 1.58? To the right of 0 or to the left of 0? Of course, it's a positive number. Mark somewhere. Not very kind of exactly where is 1.58. Just mark a line and write here 1.58. This number is actually what? Your z-score. Your step 1, correct? Now, reading less than 1.58. Which area we are talking about? Less than 1.58 is this area, correct? Now, if you are using your table, correct? If you are using your z-score table, go to positive z-score, correct? In this table, the top row and first column shows your z-score, correct? And the body, all these numbers, is the area on the left side of z-score. Look at the top. These numbers, any number that you pick from here, they shows this area on the left side of z-score, not to the right side of z-score, correct? Right now, I need a positive z-score. I have to go to this table, right? Because my z-score is positive. What I do, I'll find 1.58. The column shows up to 1 decimal. I'll move from here this way, and I'll find 0.8 this way, 0.08. Wherever these two meets, like this, that's my z-score, 0.9429. It means the area, this area is 0.9429. Correct? It means the probability of reading of this thermometer is 94.29%. Correct? I'll stop the lecture. I'll come back for the second part of this lecture and I'll explain how to use calculator and we will do more examples. Correct?